Crafts that travel millions of kilometers, crossing the boundaries of solar system in their seemingly endless journeys into the vast expanse of space. Rockets that soar high into the skies, ferrying these crafts on their missions. The thousands of man-made satellites that continuously orbit our Earth, bringing information and entertainment to our living rooms and rescuing us from disasters. Have you ever wondered how our rockets and spacecrafts find their way without getting lost in the vastness of space? How do they manage to travel through pre-decided paths to reach their targets without the aid of any landmarks or signposts? If you have, we will help you in answering those questions through this video on navigation in space missions, the science and the technology involved in the determination of the position and the velocity of these man-made wonders, that is, our rockets and spacecrafts in space. Welcome to the video. I'm Ashwati R. Krishnan from ISRO Inertial Systems Unit, and I will be taking you through the concepts of navigation. Let us begin with the term navigation. The word navigation is derived from the Latin words navis and agere, and it means to sail, to voyage through the seas, etc. Navigation is the science that involves the determination of real-time position and direction. Basically, it answers the questions, where am I? And how would I reach my destination? There are different types of navigation. In the ancient times, our ancestors have navigated with the help of landmarks, signposts, and through the identification of objects that were familiar to them. They also used to observe the position and motion of the sun, the moon, and the stars to guide themselves through uncharted territories. This form of navigation, known as celestial navigation, is still in use for terrestrial and interstellar navigation. A familiar example is the identification of true geographical north by spotting the pole star or the Polaris. The Southern Cross constellation and the Orion constellation helps us to navigate in the southern hemisphere. Except for the pole star that remains apparently stationary with respect to the Earth's north pole, all the other celestial bodies appear to be moving continuously in the sky. For example, the determination of true east or west is not possible by observing sunrise or sunset alone, because sun rises and sets in the true east or west only on the equinoxes. On all other days, sun rises either in the northeast or in the southeast. This makes celestial navigation extremely difficult in finding directions other than the north manually. Celestial navigation using instruments began in the Middle Ages. The sailors who voyaged through the seas started navigating with the help of instruments such as the magnetic compass, sextants, and chronometers. The operating principles of many of our modern-day navigation systems that are used in aircrafts, rockets, ships, and submarines derive from these medieval instruments. Dead reckoning is another commonly used navigational technique wherein no external aids or landmarks are used in determining the location. The migratory birds and animals that travel thousands of miles through dense forests, vast oceans, and prairie deserts, even crossing continents in their journeys, utilize this technique for navigation. In dead reckoning, the final position and velocity of an object can be determined with only the knowledge of its starting position, velocity, and the total time taken for the journey. This does not require any external references. Let us summarize the navigation techniques that we have discussed so far. Consider an example of navigation in our day-to-day life. How would you navigate yourself from your home to school using one of the techniques that we have discussed before? 1. Navigating with the help of landmarks or signs such as buildings and high-rises. 2. Finding a position and direction relative to the sun, moon, and the stars. And 3. By dead reckoning. Apart from these familiar techniques, we also use satellite-based navigation and inertial navigation to determine our location. We will learn more about these techniques as we go further. In general, space missions can be thought of as having 4 stages, starting from their launch till the accomplishment of their final mission goals. In the first stage, that is the launch stage, the launch vehicle carries the satellite to a predestined orbit by traveling through a predetermined trajectory. Satellites that are launched for specific applications such as remote sensing or communication have only 2 stages. In the second stage, these satellites are controlled so as to maintain their orbits. Maneuvers are done to change the orientation of the satellite to meet specific requirements. The third and the fourth stages are applicable to interplanetary and re-entry missions. In interplanetary missions, the satellites are first placed in geocentric orbits. Then, the orbits are raised in steps to reach a heliocentric transfer orbit. From these sun-centered orbits, they are taken to orbits specific to that of the desired planet, asteroid, or other celestial bodies that are to be explored by the mission. The fourth and the final stage applies to re-entry missions. This involves the entry of the craft into the atmosphere of the celestial body, or sometimes a re-entry to Earth and landing at previously decided landing locations. Let us see how these crafts navigate through the different mission stages. The rockets experience translational as well as rotational movements due to the various forces that are acting on it during the launch. Translation simply means moving from one location to another. We define the orientation or attitude of the rocket by the amount of rotation of the parts of the rocket along the roll, pitch, and the yaw axis. To guide a rocket to its final destination or orbit, its instantaneous location has to be determined, differences between the actual and the desired position has to be computed, and the errors are to be corrected. These functions are performed by the navigation, guidance, and control systems of a rocket respectively. Navigation methods used in our launch vehicles are mainly based on inertial navigation techniques that are aided by satellite-based navigation. Inertial navigation systems are highly accurate, self-contained, and work based on the principle of dead reckoning. In these types of navigation systems, the position, velocity, and the angular rates of the launch vehicles and crafts are expressed relative to inertial reference frames. Inertial reference frames are non-accelerating, non-rotating reference frames in which the Newton's laws of motion remain valid. According to Newton's laws of motion, a body experiences an acceleration or a change in its velocity when it is subjected to an external force. Imagine a stationary observer observing the motion of the children in the lift. The stationary observer computes the force experienced by the kids as F is equal to mg plus ma, where m is the mass of the body, g is the acceleration due to gravity, and a is the acceleration of the lift. When we stand on the ground, we experience a force F is equal to mg due to Earth's gravitational pull. The reaction force R is equal to mg helps us to remain in place. According to Newton's law, an additional force F is equal to ma is required in order to generate an acceleration a. Now, consider how one child computes the forces acting on the other. Since there is no relative velocity between the children, the girl computes the force on the boy as F is equal to mg. This is not in line with the Newton's laws of motion. This happens because the lift is accelerating and hence it's a non-inertial reference frame. While the laws of motions are the same in all inertial frames, they vary in non-inertial frames according to the acceleration of the frame. Hence, all the computations in inertial navigation systems are expressed with respect to inertial frames. Our launch vehicles have sensors like the accelerometers and gyroscopes mounted on their bodies that give us the instantaneous acceleration and angular velocity measurements of the vehicle. The navigation software processes these values to express these measurements with respect to an inertial reference frame first and then uses them to obtain the instantaneous position, velocity, and angular orientation or the attitude of the vehicle. The accelerometers measure the linear acceleration of the vehicle. These sensors have a proof mass within that experiences a reaction force due to vehicle acceleration. This force displaces a spring inside the instrument, and this displacement is sensed to determine the vehicle acceleration. The angular rates of the vehicle are measured by the gyroscopes. The gyroscopes work on the basis of the gyroscopic effect. Have you ever tried to keep a spinning top steady on its axis without it falling to the ground? If you have, you might have observed that the top cannot be maintained steady unless it is spinning. This is a perfect example of the gyroscopic effect. Under this effect, when a rotating body experiences a torque about an axis that is perpendicular to its spin axis, it starts to rotate about a third axis which is perpendicular to both the spin and the torque axis. In our spinning top example, when the spinning top experiences a torque due to the gravitational pull, it starts rotating about the third axis without falling down. There are different types of gyroscopic sensors based on various technologies such as the electromechanical and the optical gyros. Basically, the sensors in the launch vehicles and satellites contain a spinning wheel mounted on a gimbal. The gimbal allows rotation about an axis perpendicular to the spin axis. When the gyro case experiences a rotation, the gimbal moves and the movement is sensed to determine the angular rotation of the vehicle. Since the inertial navigation system works by dead reckoning, the navigation errors accumulate over time due to sensor and computation errors. To overcome the limitations of the inertial navigation systems, satellite navigation is used along with inertial navigation, especially in long duration missions. Satellite-based navigation relies on constellations of satellites such as the Global Positioning System or the GPS and navigation with Indian constellation NAVIC to determine location. This works based on a method known as 3D trilateration. The navigation satellites at known locations contain transmitters that emit signals at the speed of light. The receivers on the launch vehicles and satellites receive these signals and determines the exact distance between the satellite and the receiver if the accurate time between the transmission and the reception of the signals are known. Let us see how we can determine the exact position of the person in this image with the help of satellite-based navigation. Suppose we determine that the person is at a distance r1 from the first satellite. Then we can assume that he must be somewhere on the surface of an imaginary sphere with a radius r1. If we know the distance r2 from a second satellite, we can bring down the uncertainty of the probable location to an area of intersection of the two spheres. We can determine the exact location if we have a knowledge of the distance r3 from a third satellite. However, to determine the exact location, we need information from more than 3 satellites. With this information, we can determine the latitude, the longitude, and the altitude information of the vehicle. For this purpose, highly accurate atomic clocks with a precision of a few nanoseconds are used in the satellites to measure time. Satellite attitude determination systems employ inertial, satellite-based and celestial navigation methods among others. Compared to a launch vehicle that has to operate only for a duration of a few minutes or a few hours, a satellite has to operate in its orbit for many years. Hence, the satellites use information from star, sun, and earth sensors along with gyroscopes and satellite-based positioning information. The star sensor has a camera in it which images the celestial scene in its view of sight. The captured image is then compared with the star catalogs stored in it to determine the exact attitude of the satellite. Magnetometers are also used as attitude sensors in satellites which determine the satellite attitude with reference to the Earth's magnetic field. Based on the attitude information, the control system in the satellite employs the actuators to correct the attitude errors. The spacecraft actuators, such as the reaction wheels and control moment gyros, help in maintaining the attitude and orbit of the satellite. They are also used to change the attitude of the satellite to orient the satellite antennas, cameras, and the solar panels for efficient power generation. Navigation in interplanetary missions differ from that of the launch vehicle and satellite navigation discussed so far. Generally, in interplanetary missions, the launch vehicles take the satellite to an Earth-centered, that is, a geocentric orbit. Thereafter, the orbit is raised in steps to take the craft to a transfer orbit around the Sun. These crafts that move with very high kinetic energies have to be slowed down precisely in order to maneuver them to enter their destined planetary orbits. Even a delay of 30 seconds in the slowdown could result in an error of about 3 lakh kilometers in the orbit achieved. to travel millions of kilometers and then to land in their predestined landing locations within a few meters. These demands make the planning and execution of these long duration missions extremely complex. We depend on radio navigation to determine the position of these crafts in the interplanetary missions. A network of giant radio wave antennas at various locations around the globe, also known as the Deep Space Network, is used for radio navigation. Radio navigation uses techniques such as Doppler ranging, delta differential one-way ranging, etc. The phenomenon in which an apparent variation is observed in the signal frequency when there is a relative motion between a signal source and observer is known as the Doppler effect. We know the frequency of the signals that are emitted by a satellite. By sensing the frequency variations due to the relative motion of the satellite, the actual satellite velocity can be computed. By determining the time elapsed between the transmission of these signals that travel at the speed of light from the satellite and its reception back from the satellite, we can determine the exact location of the satellite. In landing missions, we enter the fourth stage, that is, atmospheric entry of the craft. Position determination mainly depends on video navigation. The velocity of the craft is reduced to a minimum as it is brought closer to the predetermined landing location. We might be having an approximate map of the landing location based on our previous observations. The images from the various cameras help us to land and to make the rovers move, avoiding the obstacles in their path in the new celestial body. Instruments like the laser Doppler velocity meter and laser altimeter also helps us in the navigation. Man's curiosity has led him to explore new lands, even crossing the vast oceans. When it took him beyond the skies, the space age dawned. Highly accurate and precise navigation systems are extremely crucial in our quest to explore the unraveled secrets of space and to discover new and exciting worlds. This video was brought to you by Sri Thanesh S. and Sri Prashant Krishna K. of ISRO Inertial Systems Unit along with me. Thank you.